Welcome back. I'm Muggsy, and today I'm going to explain the main types of chemical bonds. If you've made it to this video, you're probably familiar with both ionic bonds at this point and covalent bonds. We're going to talk a little bit about the differences between those, as well as any additional bond types that you haven't encountered yet. You'll have learned at this point that of the elements in the periodic table, they correspond to three large categories. The first are the metals, over at the left-hand side in the bottom of the periodic table. The nonmetals at the top right-hand side of the periodic table, and hydrogen. And then of course the metalloids, which are kind of at the interface between the metals and nonmetals, and sometimes behave like metals and sometimes behave like nonmetals. We'll also have learned at this point how whether something's a metal or a nonmetal determines the kind of bonds that form between the various atoms. For instance, we'll have learned just recently that if you have a nonmetal and you bond it to another nonmetal, that's a covalent bond, and that forms covalent compounds. We also learned not so long ago that if you have a nonmetal and you bond it to a metal, that's an ionic compound. Ionic compounds are formed when a metal bonds with a nonmetal, or in some cases with polyatomic ions. I'm going to add one more example today, and that is if you have a metal and it bonds with another metal, this type of bond that we're learning about for the first time is called a metallic bond, and these are called metallic compounds in some cases. Now you already know how ionic and covalent compounds work. With ionic compounds, the metal gives up its electrons to the nonmetal. With covalent compounds, nonmetals share valence electrons. Metallic compounds are very weird and kind of new and different, and I'll explain how they work right now. If I had a bunch of, let's say, iron 3, it's got 3 valence electrons. Here's another one with 3 valence electrons. Here's another one, it's got 3 valence electrons. Well, there's no real way through conventional ionic and covalent bonding that these irons can become stable. They can't really share these, because if they do, even if they formed single bonds on all 3 of these sides, they would still only have 6 out of 8 valence electrons, and they're not going to want to share anyway because they're not very electronegative like most nonmetals are. And if they were to give up their electrons, well then who would give up and who would receive? It doesn't really make sense. Instead, what happens is they can all kind of share these valence electrons in kind of a big soup. So they all roughly have access to these valence electrons. So if we have enough irons here, then each one of these irons can basically have access to 1, 2, 3, 4, 5, 6, 7, 8 valence electrons by just kind of being suspended in a big soup of electrons. Sometimes we hear this referred to as a sea of electrons. And that's actually enough to stabilize a metal. So that's how you can have a bar of metal, a bar of iron, for instance, that doesn't just disintegrate and fly away because it doesn't want to be bonded to each other. They kind of share their electrons in a big chaotic fashion. It's much harder to predict exactly of what that's going to look like we could with a covalent bond, but just know with metallic bonds, these electrons are held together in a big sea, and because these electrons are constantly moving and in flux, electricity can conduct through these metals really well, because that's all electricity is the movement of electrons. So metallic bonding forms these stable metals and it's also responsible for many of the properties of metals, such as their ductility and their conductivity and that kind of thing as well. Metallic bonding works with a bunch of metals that are from the same element, like with our iron here. It also works with different elements, like maybe you've heard of like copper and let's say tin. Existing together in a stable arrangement, Just like we have a bunch of irons, we can have a bunch of coppers and tins all together. And of course, when you have more than one metal element bonded together through metallic bonding, that's what's known as an alloy. And this particular alloy of copper and tin is called bronze. You've probably heard of it before. It's okay if you haven't. It's not something you need to have memorized for my chemistry class. It's just something that's kind of useful to know about this metallic bonding. So metallic bonding, once again, unlike ionic bonding, it's not metals giving up their electrons to nonmetals because there are no nonmetals. It's also not two or more nonmetals sharing like covalent bonding because there aren't any nonmetals. It's just metals kind of sharing their electrons very loosely in a chaotic sea of electrons that allows them to exist in a stable unit. So let's outline those major types of bonding that we've just gone over. The first one that you've learned for quite a while now has been ionic bonds, which form between a metal and a nonmetal. The one that we just went over, the newest one to you, are metallic bonds, which are between more than one metals. And then the other one are covalent bonds, which exist between one or more nonmetals. Now, the new thing that I would add is there's really, I guess, 4 bond types, because we're going to break covalent bonds into 2 categories. And you probably haven't heard about these yet. We'll learn about them right now. Polar covalent bonds and non-polar covalent bonds. Now, what do these terms mean? Let me explain. Let's look at the example of 2 different covalent compounds. If we have hydrogen bonding with chlorine, they're going to form a single covalent bond here. That will make this hydrogen stable, it'll make the chlorine stable, and we'll have the stable compound HCl, also known as hydrochloric acid. If we have 2 chlorines, kind of a similar process, they're going to share this electron here with each other. So this chlorine will share this one. This chlorine will share that one. It'll become a single bond. They'll both have 8 out of 8 valence electrons now. They'll both be stable. And this will be the stable molecular compound, Cl2, which we just call chlorine gas. Chlorine doesn't exist by itself in nature. It exists bonded to other chlorines because that makes it stable, or bonded to other things like hydrogen or sodium or anything like that. Okay. Now, what's new here is in both these cases, the electrons are being shared. But if I were to ask you, if you look at this Cl here, where are the electrons? Are they closer to this chlorine here? Let's call this chlorine 1. Or are they closer to this chlorine here? We'll call that chlorine 2. Or are they exactly in the middle? The answer is they're exactly in the middle. They're right between the 2 because these 2 chlorines are identical. They have the same strength that they're pulling those electrons towards them. And they're both very strong. Chlorine's a very strong electronegative element, so it's going to want to pull on those electrons really hard. But they're equally matched, so those electrons are going to exist directly in the middle of them. So they're not going to be closer to one atom or the other. And we call this a non-polar covalent bond. Because if you think of the poles, like the North Pole and the South Pole, if you were pulled closer to one pole or the other, that would be polar. If you're not pulled towards either pole, if you're hanging out at the equator, you're non-polar, you're in the middle. Just like we said, the electrons here are right in the middle between those 2 chlorines. Now that's actually not the case over here with our HCl. If you actually go to the periodic table and you look up chlorine and hydrogen, you can actually see their electronegativity values depending on which periodic table you're using. If I'm using the learnsomething.at periodic table, I can see that my chlorine here has 3.44 for its electronegativity value, Those were determined by Linus Pauling, and so sometimes we call those Paulings as the units, but you don't need to use any unit at all. We'll just call that 3.44 for electronegativity. Now, what is electronegativity again? Remember, it's how badly an element wants electrons and how strongly it pulls those electrons towards them. Why does that have such a high electronegativity value? Because chlorine has 7 out of 8 valence electrons, so if it gets just one more, it'll be stable, so it really, really wants one more. All the halogens have really strong electronegativities, and in fact, electronegativity gets bigger as you move to the right across the periodic table, and then also as you move up the periodic table. Okay, hydrogen. What's the deal with hydrogen? Well, if we look up hydrogen in the periodic table, it has an electronegativity value of 2.2. So it's not nothing, it's not super low, but it's much lower than 3.44. So hydrogen is pulling on those electrons and it's much weaker. So this is basically a tug of war between hydrogen, a really weak guy, and chlorine, a guy that goes to the gym and works out all the time. That means those electrons are going to be much closer to the chlorine than they are to the hydrogen. And in fact, what that does, if the electrons are closer to the chlorine, it almost acts like an ionic bond and it almost gives that chlorine a negative charge. We call that a partial negative charge, and we use this lowercase delta. It's a really weird looking symbol to represent that. And this hydrogen, it's kind of like it's giving up its electrons. It still has access to them, but they're closer to the chlorine than they are to the hydrogen. So in doing so, it almost gains a positive charge. It gains a partial positive charge, and we use that little lowercase delta to represent that. So, because the electrons aren't in the equator here, they're closer to one of the poles than the other, we call this a polar covalent bond, and this is a polar covalent molecule. Now, both polar and nonpolar, it's important to note, are types of covalent bonds. Polar and nonpolar aren't something that happen with ionic bonds. Ionic bonds, I guess you could say, are so polar, they're super polar. They're like beyond polar. But with covalent bonds, they can break down to be either polar or nonpolar. Now, I just said 2.2 is less than 3.44. That's how you know it's polar. There's actually a more specific number, and that number is 0.4. If the difference between the two electronegativities is greater than 0.4, or in some cases equal to 0.4, it's going to be polar. If it's less than 0.4, then it'll be nonpolar. In this case, I didn't actually have to do any math because I know that chlorine is going to be exactly as strong as chlorine, but I could have done some math. I could have said look this up in the periodic table, the electronegativity of chlorine is 3.44, the electronegativity of this chlorine is 3.44 because they're the absolute same. 3.44 minus 3.44 is 0. 0 is less than 0.4, so it's nonpolar. 3.44 minus 2.2 is what, 1.24? 1.24 is greater than or equal to 0.4, so it's polar. Let's look at one or two more examples and you'll really understand this difference between polar covalent bonds and nonpolar covalent bonds. Okay, here you'll see I have two more covalent compounds, sulfur difluoride and hydrogen gas. Sulfur bonded to two fluorines and hydrogen bonded to itself. Let's investigate if these are polar, nonpolar, what's going on. So sulfur, if we look it up in the periodic table, we can see that its electronegativity is 2.58. That's kind of like, I guess, a medium-high electronegativity. Fluorine, however, has an electronegativity of 3.98. That's pretty much as high as they get. Fluorine has an absolute massive electronegativity, and you would actually predict that because, again, electronegativity increases as you move to the right in the periodic table and up the periodic table, and fluorine is basically in the upper right of the periodic table, with the exception of the noble gases. The noble gases, as you might guess, have no electronegativity pretty much. They don't want to gain electrons at all because they're totally stable just the way they are. Okay, so which one of these two is pulling more strongly on those electrons? If you said fluorine, you are correct. It has a higher electronegativity, so the electrons are going to be a little closer to the fluorine than the sulfur, giving it a partial negative charge, giving that sulfur a partial positive charge. This fluorine, same thing, it's going to get that partial negative charge. Specifically, you could actually calculate the difference between these two and see that it's greater than 0.4. So you could say 3.98 minus 2.58 is 8s are going to cancel, 0.4, 1.4, right? So that's still a big enough difference that this is going to be a polar covalent molecule. What about here? Well, I'm not going to do any math at all. I'm not going to look up any electronegativities or nothing like that, because I know that if hydrogen is in a tug of war with itself, it's going to be a tie. Hydrogens are all identical. There's isotopes, but those aren't really going to have any effect. And so neither one of these is going to have more electronegativity than the other, so the electrons are going to be right in the middle, so this is going to be a non-polar molecule. Let's review these main types of chemical bonds that we just learned about. For instance, if we had a bond between metals, that would be a metallic bond. And we can describe the structure of a metallic compound as a bunch of atoms suspended in a sea of electrons. The electrons are all kind of freely flowing around these different atoms that hold the structure of the metal together. Now, because the metal is kind of held in this structure by the sea of electrons, they tend to be solid at room temperature. That means they have a relatively high melting point. And if you think of metals like iron or nickel or tin, you know, they tend to be solid, but if you melt them down under really, really high temperatures, they can become liquids. Because the electrons can move freely, they are very electrically conductive. We call that conductivity. And then if you think of a bar of metal, if you hit it with a hammer, it's not going to break or shatter, it'll kind of dent, right? And it's a lot of metals, if you beat it enough, you can kind of beat it into a sheet. We call that malleability. You could also maybe pull it into a wire. That's called ductility. They tend to kind of, instead of breaking apart, they tend to kind of maintain their shape. So we'll just say high malleability. There we go. Oops. Okay, next, if we had, instead of metals, let's say we have a metal and a non-metal. Well, that would be the first bond that we learned about, ionic bonds. And remember, the structure of an ionic compound is this crystal lattice of cations and anions suspended in this giant crystal with equal and opposite charges that attract them and hold those atoms in this nice, tight crystal lattice structure. Now, because they're in this really tight crystal lattice structure, they have an even higher melting point, because it's hard to break that apart, than metallic compounds. So I'll put highest melting point. Ionic compounds do conduct electricity, but only when they're dissolved in water. And if you think of a crystal, if you hit it with a hammer, it's not going to be malleable. It's not going to form a sheet. It's going to break apart and shatter. And that's exactly true. Ionic compounds are brittle. One other thing I would say about the physical properties of ionic compounds is I just said that they are conductive for electricity when they're dissolved in water. That implies that they can dissolve in water, and we say that they are water soluble. Soluble in water. So if you have salt and you put some in your water, you won't see little crystals anymore, especially if you stir it up. It'll eventually just look like water because the salt crystals dissolved in the water, and that's true of almost all ionic compounds. Okay, finally, the most recent one we learned about is if we have two or more nonmetals, that would be a covalent bond. But we are going to break that apart into our two types of covalent bonds we just learned about. So for instance, if it was amongst two or more nonmetals with different electronegativities, oh, that's just the worst spelling. The worst handwriting. Sorry, I'll try a little better. Electronegativity. Well then, we call that a polar covalent bond. And of course, if it's amongst nonmetals with similar or the same electronegativity, then we call that a non-polar covalent bond. The structure of these two is basically the same. Our metals exist in this big kind of sea of electrons, and our ions, our ionic compounds, exist in these crystal lattices. Our covalent compounds are different. They exist as separate molecules. So water, which is a polar covalent compound, if you have a glass of it, it's not in that glass of water, it's not a bunch of H's and O's stuck together in this big lattice or H's and O's surrounded by a sea of electrons. It's individual little H2O molecules, just a bunch of those all stacked together and held together with these intermolecular forces that you'll learn about a little bit later. The properties of nonpolar and polar covalent compounds are actually different. Nonpolar compounds, remember, have kind of no charge to them because the electrons are right in the middle. A polar covalent compound is going to have a slight positive and slight negative charge because the electrons are pulled a little bit more closely to the more electronegative atom. What that means is you can think of them as being a little bit more like ionic compounds. They're a little bit like nonpolar covalent compounds and a little bit like ionic compounds. They're kind of in the middle. So let's start by just talking about our nonpolar compounds. Our nonpolar compounds, they're kind of the opposite of these earlier ones. They have a very low melting point for the most part. A lot of our nonpolar compounds exist as liquids, or some exist as gases, so they melt at pretty low temperatures. They tend to not conduct electronegativity, not conduct electricity, non-conductive. They tend to be insoluble in water. If soluble means it dissolves, insoluble just means it doesn't dissolve in water. They do dissolve in other nonpolar substances, but not in water. And then in terms of whether they're brittle or not, yeah, they do tend to be brittle just like these other ones, but there's a relative high range of the physical attributes of these covalent compounds. So we'll just ignore whether they're brittle or malleable or anything like that. Polar compounds, again, they're a little bit more like ionic compounds than these nonpolar compounds. So they do have a low melting point. But not quite as low as this nonpolar, so let's say lowest here. In terms of their conductivity in water, they actually are conductive in water. Just like an ionic compound. Because, like I said earlier, they have a partial positive and a partial negative charge, just like an ionic compound has a full positive and a full negative charge. And these charges enable the electrons to flow through a solution with these polar molecules dissolved in it. Are they soluble in water? Yes, they are soluble in water. Similar to these ionic compounds. There's a lot of similarities between ionic compounds and polar covalent compounds. Okay, so the reason I like to put these in a table is hopefully you can see that there's kind of some trends going on here. The first trend I would say is the more metallic character we have over here, the more we have certain traits like a really high melting point and high electrical conductivity, high malleability. As we move into the middle here with ionic compounds and polar covalent compounds, there's some metallic character, but it tends to go away and we're moving more towards nonmetals. And so in that case, we end up with, you know, kind of lower melting points, not the lowest, but lower. They're electrically conductive, but only when dissolved in water. And they tend to be a little bit more brittle than these really malleable metals. And then once we get all the way over here to the right to our non-polar covalent compounds, these have pretty much no metallic character. It's only made of nonmetals, but so are polar covalent compounds. But those nonmetals don't even have a strong electronegativity difference. So because of that, they have a really low melting point, they don't conduct electricity, they don't dissolve in water. They're kind of as far away from metallic compounds as you could get. So all of our chemical compounds out there, we can sort into these 4 categories. In reality, it's kind of like 3 categories, right? Metallic, ionic, and covalent. But I like to break it into 4 because as we can see, there's actually quite a lot of differences between polar covalent compounds and non-polar covalent compounds. Finally, I'd like to talk about metalloids because it's easy to get confused because metalloids, as I talked about earlier, are kind of like a metal and kind of like a non-metal. So what do? Do they do metallic bonding? Do they do ionic bonding? Do they do covalent bonding? Well, it just kind of depends on the situation and the metalloid in question. Metalloids are really tricky and it's hard to predict what they're going to do. So typically your teacher or professor will just kind of tell you what any given metalloid is going to do. For instance, if we have silicon and oxygen and they come together, we get the compound silicon dioxide, which is a covalent compound. But if we have arsenic, and let's say that's arsenic with an oxidation number of 3, and oxygen, and they come together, this has a +3 charge, so there's going to take 2 of them to every 3 oxygens, which have a -2 charge. And we're going to get the compound arsenic oxide, or arsenic 3 oxide, I guess, which is an ionic compound. So it really just depends on the metalloid in question. And it's even trickier than that because metalloids can sometimes do one thing and sometimes do another. That's one of the beautiful things about metalloids, is pretty much all of our computer chip technology is based off of metalloids, because if they can conduct electricity some of the time under some conditions, but not under other conditions, we can have them conduct and not conduct and conduct and not conduct, and we can make a binary signal of that electricity passing through the metalloid, of which all of our computer code and all of our modern technology with regard to computers is based on. So metalloids are really tricky. Sometimes they can behave, if you bring a metalloid and a non-metal together, you get a covalent bond. Other times, if you bring a metalloid and a nonmetal together, you get an ionic bond. Typically, if you're my student, I usually don't even do many examples with metalloids, but if I did, I would tell you that it's going to form a covalent bond or an ionic bond, something like that. Okay, you've reached the end of the video. Thank you for watching this far. I'll do a really quick review of our 4 main bond types just so it's really sticky in your brain and you won't forget it anytime soon. If we have metals and they bond together, that's called a metallic bond. Metallic bonds form basically big seas of electrons, which are responsible for all the physical properties of metals. Their high conductivity, their high malleability, their high melting point, that sort of thing. If we have a metal and a non-metal coming together, that's an ionic bond. Ionic compounds tend to exist in this crystal lattice structure of cations and anions forming a big old crystal. Because of that structure, if you were to hit it with a hammer, it's very brittle. Ionic compounds do dissolve in water, and they do tend to conduct electricity in water. One other thing, ionic compounds aren't just metals and nonmetals. Sometimes they're formed by polyatomic ions, so don't forget your polyatomic ions. Next, if we have 2 or more nonmetals coming together, that's a covalent bond. Covalent compounds are not so much like the metallic and ionic compounds. They tend to have a pretty low melting point. They tend to be a little bit less electrically conductive, all that kind of thing. But before we talk about those properties, let's remember that there are actually 2 types of covalent bonds. If the 2 elements kind of share the electrons equally, and they're in an equally matched tug of war, we would call that a polar covalent compound. I'm sorry, a non-polar covalent compound. And if one of the elements in the bond has a much higher electronegativity than the other, it'll pull the electrons closer to itself and form a polar covalent bond. Polar covalent compounds tend to be a little bit more like ionic compounds because polar compounds have partial charges which are similar to the full charges of an ionic compound, whereas non-polar covalent compounds tend to be very unique and very different from all these other ones. They, for instance, aren't soluble in water, they don't conduct electricity, that sort of thing. Okay, hopefully that's enough to know to get you started on these main types of compounds, metallic, ionic, and covalent, and then of course covalent can further be broken into polar and non-polar. Thanks for watching, I'll see you next time.